we go. All right. So yeah, our next speaker is Debra Fischer, Yale University, and she will talk to us about extreme precision radial velocities.
That's right, very extreme. So first I want to thank the organizers. I have been coming to this school for a long time, first as a postdoc, then as a professor, and Chaz Beichman really deserves a lot of credit for having the vision to make sure that this has happened every year for such a long time now. One of the themes that I've heard is that these observational techniques, transits, direct imaging, are complementary. And that's true. I'm not going to say that, no, the radial velocity technique is really all you need. But what it means is that on these plots where you have mass or radius on the y-axis as a function of either orbital period or semi-major axis on the x-axis, we have a huge pile of planets, right? You can see that each technique is sensitive to a different part of that parameter space, but we actually have very little information about planetary architectures. Other than the solar system, I can't tell you another star, and sort of map out its entire architecture of planets. So I've been working on Doppler surveys since 1997. I will say since at a time when we called these planet candidates and when there was a lot of doubt about whether or not they were really planets. Although this technique requires a lot of patience because you have to map out a full orbital period, at least one, it's a fairly inexpensive technique. It's ground-based. We don't have to send a mission into space. And I've been the PI now for 3 different spectrographs, the latest one being Express, which is at the Lowell Discovery Telescope. And I can tell you, and I hope to convince you in this talk, we have entered a new era of extreme precision radial velocities in the last few years. And I think that means that we have a pathway to really starting to understand planetary architectures, to dig down and figure out how things relate. And also because we focus, because of brightness limitations, on bright nearby stars, it means that we're getting some planets that I think Daniel would say are high value planets like 55 Cancri E, where there's been a big payoff. So after this presentation, I hope that you'll understand what kind of exoplanets can be detected with the Doppler method, how radial velocity precision has evolved over the past 3 decades. And I want to show you a breakthrough radial velocity result, I think, on Barnard's star, which I think is a game changer, really introduces in a convincing way a new era for Doppler observations. And then I'll also highlight the key challenges and give you my future predictions about what's going to happen with this technique. So what kind of planets can we find? Just so we're all on the same page, what we're observing is the star, and we're measuring the radial velocity over time by watching the shift of the spectrum. And when you see a cartoon like this, you think, that's pretty easy. I can see those spectral lines moving. But if we're trying to detect small Earth-like planets, the wobble is less than a pixel, far less than a pixel shift. We're talking about a shift of spectral lines across several silicon atoms in our detectors, right? So we need incredible stability to be able to do that. An amplitude of 1 meter per second corresponds, which is pretty big right now. I would say is easy, corresponds to a shift of about 1/1000th of a pixel. So that's incredibly small. So the theme here is extreme, and the extreme value of extreme precision radial velocities is that, first of all, this is a technique that enables the detection of non-transiting Earth analogs. Okay, it, I think, is currently the best method for detecting Earth-like planets orbiting nearby stars, so stars that are closer than about 20 parsecs, twiddle 20 parsecs. But this is a technique that's also just limited to G, K, and M type stars. Earlier type stars, they're hot, they don't have as many spectral lines, and the lines that they do have are broadened by stellar rotation. And one of the things that I hear, one of the criticisms that I hear is, well, with the Doppler technique, you only measure M sin I. It's true. But I want to talk about the probability of different inclinations because they're not equal, right? The probability of a face-on orbit and the probability of an edge-on orbit are very different. And we really talk about, if you're talking about probability, you have to have a range of inclinations that you're going to integrate over. And so for planets that, planetary architectures or planetary orbits that have an inclination of between 90 degrees and 60 degrees, right? So fairly close to edge-on. The probability of seeing that configuration is a half, right? So half of the planets that we look at are going to be oriented like this. And you can ask a question about that if you don't understand it at the end. And that means that about half of the radial velocity planets that we detect will have a true mass that's related to M sin I, that's only a little bit bigger than what we measure as M sin I. So it's 1.15 times M sin I, like you'd say that's the same. For planets that have orbits between, 30 degrees, why did I choose that? 30 degrees and 90 degrees. Oh, I know. Yeah, so almost face on 30 degrees and 90 degrees, right? And 87% of them will have that configuration. And even then, we're just within a factor of 2. Okay, thanks. Of the true orbit. Sorry. So a small fraction of otherwise detectable amplitudes are going to be missed because of orbital inclination, right? But it's a much lower sensitivity to inclination than, for example, transits. And statistically, the true planet masses that we get are within a factor of 2 of what we measure as M sin I. Okay, so precision matters a lot, and I've spent, I would say, my whole career, the whole last 28 years now, working on trying to improve precision. So here you see, let's see, I guess, did I not have the equation up here? For an semi-velocity amplitude K of 3 meters per second, you can see what we can detect, only stuff that's above these curved lines, right? And so I show here the planet mass on the y-axis, the semi-major axis on the x-axis, and I have highlighted the habitable zone, so you can see what kind of planets we can get. So if my precision is a few meters per second, I'm only getting planets that are like Saturn, like Jupiter, big planets out at the habitable zone distances. If I can measure amplitudes of 1 meter per second, I'm getting down to 10 Earth masses in the habitable zone, right, of a solar type star. And if I can measure amplitudes of 0.4 meters per second, now I'm really starting to get closer to an Earth. The amplitude of 0.1 meter per second, so the amplitude that Earth, the reflex velocity induced by the Earth on the sun, right, requires precision levels that we're not at yet. Okay, but if I look at an M dwarf, because the amplitude scales inversely with the mass of the star, so the bigger the star, the smaller the amplitude, but go to a low mass star, then measuring an amplitude of 1 meter per second, which is pretty easy, in the habitable zone, gets me down well below the mass of the Earth. Right? So these are very promising stars to look at as long as they're habitable. One difference, of course, between the M dwarfs and the G dwarfs, the solar type stars, is the brightness of these stars, and that makes a big difference. I have a 4-meter telescope that Express is connected to, and that means I can only look at bright stars. So maybe we have a couple of M0 stars in our sample, but you have to use something like Keck and the Keck Planet Finder to really be able to drill down and see these much fainter stars. Okay, so since I've been here for a long time, how has the radial velocity precision evolved over the past 3 decades? Well, what matters again for the Doppler technique is going to be the mass of the star, the mass of the planet, the orbital period, the orbital inclination, and the measurement precision. And there is only one thing on that list that we can control, and that's this last factor. So how are we doing? It's not going forward. Yeah. It's just not advancing. Let's see how it's going. Oh. Okay.
Is that the correct one?
Yeah. Okay. So this is a little bit down in the weeds, but you have to understand this to understand the future of extreme precision radial velocities. Reaching sub-meter per second precision requires incredible stability in the instrument. Earth only induces a 9 centimeter per second signal over 1 year. And we have to also deal with the fact that we're observing the star, and the star produces radial velocity signals that are not dynamical, that come from flows on the surface of the star. So that means that our instrumental systematics have to be tightly controlled. And this is, I think, where we've made a lot of advances in the last decade. And then data systematics have to be controlled. We have to figure out a way to model stellar activity, and we made a lot of advances here. Okay, so this is in 2015, we had an extreme precision radial velocity conference at Yale. And everybody brought their data, showed their data. And so what you see here is our two plots, the same two plots for a bunch of different instruments, showing the single measurement precision on the left in the first column, and then the RMS scatter of stars. And we just cut off at 10 meters per second. So there's a whole bunch of stars that have higher scatter. But you can see that, at Lick, where we were claiming to get 3 meters per second precision in the 1990s when I was working, we did that, but only that was the best case. And there were a lot of stars that actually didn't do that well. And then here's McDonald, their high resolution spectrograph, sort of the same vintage of spectrograph. And then Keck with, I think all of these three instruments used an iodine cell for the wavelength calibration, was about 2 meters per second. So this is the battle 1990s. And then HiRes gets its, HARPS gets its very own slide because they made a huge difference in the field. They put their spectrograph in a vacuum chamber, right? And they really went all out on engineering stability. And they reached a measurement precision of 1 meter per second. We could hardly believe it, I would say, at the time. And the RMS scatter now that they're seeing peaks at about, 1.5, 2 meters per second. So that was an impressive accomplishment. And as a result, there are a number of spectrographs that then copied HARPS, right? So what do you do when it succeeds? So in the 2005, we were getting the HARPS data. And so from 2005 to, sort of 2010, we're building spectrographs that look just like HARPS, right? That are in vacuum chambers. And then we now have a new generation of spectrographs. Express is one of those, but there's also NUID, which is on Kit Peak. There's the Keck Planet Finder at Keck. There's Maroon X on Gemini. And these instruments are now getting single measurement precision that's well under 0.5 meter per second at the in the high signal to noise regime where we usually work. And we're seeing that the RMS scatter that we measure is also coming down. We're really drilling down, and we have, almost a factor of 100 improvement in this generation of spectrographs compared to the late 1990s generation. So here's a sketch showing you the radial velocity detected planets, and I'm really hoping that you don't notice that the data source is from Exoplanets EU instead of the NASA Data Archive. So I won't say anything about that, but it shows the planet mass, or M sin I, on the y-axis versus the orbital period. And then we have these lines penciled in for the velocity amplitudes that these planets would correspond to, assuming different masses of stars. So the solid line assumes a solar type star, and the dashed line is a low mass M dwarf. And you can see right here, these points right here, which I think are a game changer, right? We're starting to get down to detecting tiny amplitudes. And of course, these are around M-dwarf stars. Okay, so this is the breakthrough. Like, the first paper was published by the Espresso team, the Geneva team, last October, and then a follow-up paper from Maroon X on Barnard's star, which we followed forever. It was one of the first stars that in our surveys back in the 1990s at Lick Observatory. And you can see what they've discovered are 4 planets. They all have amplitudes of about 40 centimeters per second. The last one has an amplitude of only 20 centimeters per second. All right, now there's swimming in a sea of noise, which might look bad to you, but it reminds me of like 51 Peg B, back in 1995, except that there's 2 orders of magnitude improvement in the amplitude, right, that's detected here. So I was worried about the first time. I mean, if you add enough planets, right, you can always like have it absorb a lot of your systematics. But the fact that both Espresso and Maroon X are able to see the same thing is impressive. So I believe this result. I think this is incredible. And here's an example of what could be detected theoretically around Barnard's star, with the habitable zone for that star shown as the green band. And there are the 4 little planets, B, C, D, and E, in that system. And so therefore they can rule out a lot as well as detect a lot, really start to understand the architecture of the system. The detection confidence is, we often use this, I don't really like it, but the sort of confidence level or signal to noise of the confidence level of K, the velocity amplitude, divided by sigma, our error bars, times the square root of n. So that means observe more and more, get more and more observations, and you can really improve your detection confidence. And so, and we consider a signal to noise level of about 5 to 7 now as being robust. It corresponds to an FAP, a false alarm probability, less than 1%. The problem with this is that I can have a given K, I can get 1 million observations, but if I don't sample the phase of the time series data well, then it doesn't really mean anything. But I would say that in the case of Barnard's star, many orbital periods were observed, right? These are 4-day periods. The observations spanned 4 years, impressive, right? And the signal to noise, the confidence levels are incredibly high. So, 50 or 14, these are very high. I believe this result. I believe it means that we can start to detect signals that are 30 or 40 centimeters per second, which is astonishing. All we have to do is be able to control understand and model out the stellar activity and control the instrumental stability. I will say that we are not quite there yet on both of these, but this new generation of instruments has told us what we need to do to get there. So extensive work has been done on each of these challenges, and they're each worth many lectures. I want to for just immediately at first, I don't want you to look at the line that goes through the data, but just look at the data points, the little square boxes that are plotted there. Radial velocity in meters per second over time on the x-axis. It means that the radial velocities for Barnard's star are scattering by, almost plus minus 4 meters per second. And yet they're pulling out 4 planets with amplitudes of 0.4 meters per second. They can only do that by looking at correlations between environmental parameters and velocities for a bunch of stable stars, and by using a technique to model the stellar activity, which they've done here. They've used a Gaussian process regression that's a double harmonic. The kernel that they use is the 2 harmonics are the rotation period of the star, which is 150 days, and half of that. So Yeah, so progress is being made on both of these. Now I want to show you the bad thing. This is express data. This is like not something I'm really proud of, but this is the truth. So we take all of our stable stars, we plot, just throw down the radial velocities of them. You can't, they all the same color for like 20 different stars. And you can see that systematically the velocities are changing as if the stars are some like quantum entanglement and the stars know what the other stars are doing. And that's always a bad sign. But then I've shown you in black, what I've calculated are the line bisectors of our laser frequency comb, which are starting to introduce a little bit of skew when there are thermal changes in the instrument. And here, this big era is when we lost the temperature control in our spectrograph room. So that means we have a pathway to correcting this and to improving the velocities. That's one of the things that we're going to have to do. And if you build a spectrograph, you should put in like as much sampling of temperature and pressure as you can possibly afford, so that you can look at this. Lily Zhao, who is my graduate student and is now a Hubble Fellow, looked at this and tried to correlate this sort of, I show you two groups of before and after. So here what she's shown is the parameter that she's using to decorrelate, right? And then how well the velocities sort of straighten out afterwards. And you can see some things work well and other things don't. And so this is something that we're still working on and trying to improve so that we can get a correction for our systematic instrumental errors. Okay, so the conclusion here and my predictions for the future are that we're going to continue to be limited by stellar activity in terms of what we can extract, but the models are already improving. And there are a couple of clear leaders here. Scalpels is one of them. Other Gaussian process regression techniques are very promising. It concerns me that when we do an exercise that the different techniques aren't pulling out the same corrections, but I think we're getting to the point where there are some really clear leaders. And we have this great test case. We have solar telescopes that feed most of our high resolution spectrographs now. And these solar telescopes are ideal training grounds because we also have spacecraft that are like staring at the sun and telling us when spots, move across the surface of the sun. And we can absolutely map the radial velocity changes to what's happening on the surface of the sun. We'll be able to extend that to other stars. So we have to work harder on improving and monitoring the environmental stability. I mean, what we have right now with this generation of spectrographs is already so dramatically better than what we had, 25 years ago. And I think another thing that I'm impressed with is that we have this new generation of spectrographs. I list some of them here: Espresso, Express, NUID, Maroon X. And they all have different designs. And the instrument, the designers, the PIs made different decisions about what they thought was important. And yet I think it's impressive that we all understood what the tall pole in our error budget, because all of these instruments are reaching a single measurement precision of about 10 to 30 centimeters per second, right? So we're already able to reach potentially habitable Earth mass planets around M and late K dwarfs. So we're there. And I think that in the next decade, we're going to improve our instrumental stability in our modeling so that we'll get down to 1 or 2 Earth masses around solar type stars at almost habitable zone distances. This means that we can really, I've focused just on the pile of planets, right, as the habitable Earths, but it means that we can start to really disentangle multi-planet systems around other stars. And I think improve our knowledge, improve our data, our information, and our knowledge about planetary architectures. So, so that's the big improvement that we have to make is keep working on the stellar activity models and the environmental stability of the instrument. And I think that this technique will anew, be able to contribute information about exoplanets that is complementary to other techniques. So thank you.
Thank you very much, Debra. So if you have questions, please come here to the front. And in the meantime, we have a few online. So one was about a multi-planet system. How can the EPRV method be used to determine the individual eccentricities of each planet's orbit?
So by modeling every single planet, coming up with the best fit model, we can measure eccentricity as well as semi-major amplitude, as well as orbital period, as well as M sin I. But the truth is, when we get to these very small amplitudes, our ability to really measure eccentricity, is it 0 or is it 0.1, is degraded. And so there, for Barnard's star, in fact, they came up with eccentricities that were non-zero, and they ruled them out with dynamical analysis that showed that if they were non-zero, that the system would be unstable because the planets were packed together so tightly.
Great, thank you. So question in the room?
Hi, Debra. Suri from MPE. Thank you so much for the great talk and such a long journey to find us very tiny planet. My question is, could you elaborate more about dealing with stellar activities, looking from the instrumentation and modeling perspective? What would be the best ingredients or which list that you could add? Because I think this would be a great lesson learned. Also for the atmospheric study in the future, because nowadays we basically adopt PRV instrument for
Right, that's
studies.
right. Right. Well, let me first say that when you look at the old data, right, like from Lick Observatory, there was a whole bunch of stellar noise that we simply couldn't see because the error bars were large and because the instrumental systematics, maybe even more important, were not stabilized. And so we had run-to-run differences. So by building this generation of new spectrographs, which there was criticism when we kind of started down this path saying, but stellar activity is still going to limit you in what you detect, then my response was, well, yes, but you can't see it unless you get under that noise, right? You've got the quadrature sum of terms that are all about the same height. So we shrunk these other terms, and that's permitted, I think, a more accurate modeling of the underlying activity. So I think we're getting there, and the Gaussian process regression and other techniques look very promising.
Great, thank you. Yes, Chaz.
Thanks, Deborah. I guess one question that's sort of an implied things that we need to do better, instruments, stellar variability, is I think the key to that has to be cadence. And how do we get the agencies to recognize in the way that I think Didier described in his kickoff talk with his terra hunting experiment? He's just doing this every night for 10 years.
Yep.
And I don't think NASA or NSF has recognized that that's what we have to be doing.
Right. That's right. So I think that Chaz was asking about the cadence that we need, how often we need to observe the stars to be able to disentangle multi-planet systems. And for example, to be able to model stellar activity, because if there's a big time gap in your observation, you have a Gaussian process regression, which is it has some kernel that's sort of predictive, but then you hit a time gap and it doesn't know what to do in that time gap. And so if you had like the ideal case, I think Didier's idea about like every single night, I would even say put 4 telescopes around the world, right? And then as the Earth turns, we can like really continue. If we really want to learn, that's what it takes. And it really isn't so expensive. In terms of, if you think about the cost of space missions, but how do you get NASA and NSF to recognize this? I think, most of their direction comes from, after being at NSF as the division director for a couple of years, comes from the decadal surveys. So if this can be somehow elevated, it has to be a community understanding of what it is we need to do to take the next step. And also, I think, Daniel had a great point in terms of, just getting one more planet, how much knowledge does that change? How much does that give us? So we have to do a better job of making the case probably about what we're going to get at the end, given that we have all these other amazing instruments and missions.
Yeah, and there's one more question online. What are the best wavelengths for precision RV?
Oh, is that from Jacob Bean?
That's Phil Forrest.
Okay. So I think I'm mildly, okay, this just sounds so rude. I'm mildly impressed with the slightly improved performance of in the infrared. The idea is if you look at infrared wavelengths, that the contrast between the spot and the star is lower because the spots are cooler, but at IR wavelengths, you don't see the spot as much. At the UV wavelengths, you're going to see the spot moving more. Now, is it better to sort of like hide the bad stuff or to like shine a spotlight on it so that you can really model it well? And I guess the proof is going to be in the pudding and in the results. And I would say, NUID and Maroon X, which go into the infrared, are suggesting that they do have better results, better precision and stability at infrared wavelengths. It's still a little bit hard to disentangle if it's that wavelength effect or if there are other things going on though. So yeah, it's not overwhelming, I think.
Okay, thank you very much.
Yeah.
So we're out of time, but thanks, Debra, again, and up next week.